Light travels incredibly fast. It is the fastest thing in the entire universe. Nothing we know can travel faster than light. This speed is not just a record, it is a fundamental rule of nature. Think of it like a cosmic speed limit, one that nothing can break. This speed is about 299,792 kilometers per second. That is fast enough to go around the Earth more than 7 times in a single second. This incredible speed shapes how we see the universe. It also shapes how we understand time and space. Because light travels so fast, it acts as our messenger from distant stars. When we look up at the night sky, we see light that has traveled for many years. Some light comes from stars very far away. This light tells us stories about these stars. It tells us what they are made of and how old they are. But this messenger, light, has a finite speed. It does not arrive instantly. This means we always see the past when we look at distant objects. We see them as they were when the light left them, not as they are right now. To measure the vast distances in space, we use a special unit. This unit is called a light year. A light year is the distance light travels in one whole year. This distance is enormous, about 9.5 trillion kilometers. Our closest star system, Alpha Centauri, is over 4 light years away. This means the light we see from it started its journey more than 4 years ago. The universe is so big that some galaxies are billions of light years away. Their light has traveled for billions of years to reach our eyes. The speed of light is more than just a velocity. It is a cornerstone of modern physics. Albert Einstein's famous theories of relativity are built upon this idea. He realized that the speed of light in a vacuum is constant. It is the same for everyone, no matter how fast they are moving. This simple fact has profound consequences. It changes our understanding of time, space, and gravity. The speed of light is a true universal constant. It helps us unlock the secrets of the cosmos and our place within it. When we hear the word teleportation, many of us think of science fiction. We imagine people or objects instantly vanishing from one place, then they reappear somewhere else, perhaps far away. However, real-world teleportation, especially quantum teleportation, is a bit different. Scientists are not yet teleporting people or large objects. Instead, they are focusing on something much smaller and more fundamental. They are learning to teleport information. Specifically, they are teleporting the exact state of tiny particles, like particles of light. So what does it mean to teleport light? It does not mean sending a physical particle of light from one place to another instantly. Light already travels very fast on its own. Instead, teleporting light means transferring the specific quantum properties of one particle of light to another. Imagine you have a very special, unique coin. Teleportation would be like creating an exact copy of that coin's unique features onto another coin far away. The original coin's state is destroyed in the process, and a new one, identical in state, appears elsewhere. This is what scientists have achieved with light. The first successful experiments in quantum teleportation were major breakthroughs. These happened in the late 1990s. Scientists showed it was possible to teleport the quantum state of a single photon. These early experiments were complex. They required careful control over individual quantum particles. Quantum mechanics, the strange rules governing the very small, is key to this process. It allows for connections and transfers that classical physics cannot explain. These first steps were small, but they opened a vast new field of research and possibilities for technology. The excitement surrounding these initial successes was immense. It showed that a concept once confined to theory could be realized in the laboratory. Teleporting the state of a photon might seem like a small feat, but it represents a giant leap in our understanding and control of the quantum world. It is a foundational step towards powerful new technologies. These could include ultra-secure quantum communication networks. They could also include super-powerful quantum computers. The journey into quantum teleportation had truly begun, promising to reshape our future. What exactly is light? For a long time, scientists debated this question. Some thought light was a wave, like ripples on a pond. Others thought it was made of tiny particles. Today we know that light is both. It can act like a wave and it can act like a stream of particles. These tiny particles of light are called photons. Photons are like little packets of energy. They are always moving. And as we know, they move at the speed of light when in a vacuum. They are the fundamental units of light and all other forms of electromagnetic radiation. Photons are created in various ways, often when atoms get excited. Imagine an electron orbiting an atom's nucleus. If this electron gains energy, it can jump to a higher energy level. But it does not like to stay there for long. When it jumps back down to its original lower energy level, it releases the extra energy. This released energy takes the form of a photon. You see this process happening all the time. The light from the sun, the glow from a light bulb, or the screen you are reading this on, all involve the creation of countless photons. Once created, photons travel outwards from their source. They carry energy and momentum. Photons also have other properties, like polarization. Polarization describes the direction in which the light wave oscillates. Think of wiggling a rope up and down or side to side. Photons can interact with matter. They can be absorbed by atoms, causing electrons to jump up. They can also be scattered, changing their direction, like when light reflects off a mirror. Understanding these properties and interactions is crucial for controlling light in experiments. In the world of quantum experiments, individual photons are incredibly important. They are the building blocks for carrying quantum information. Scientists can manipulate single photons. They can change their polarization or other quantum states. By doing so, they can encode information onto these tiny light particles. This ability to control single photons is essential for quantum teleportation. It is also vital for developing other quantum technologies. These tiny dancers of light hold the key to many future innovations, from secure communications to powerful new computers. In the quest to master quantum teleportation, many research groups are making strides. One notable series of advancements has come from teams in Tennessee. Researchers, for example, at Oak Ridge National Laboratory and associated universities have been pushing the boundaries. They have been working on teleporting the quantum states of photons. This is not about making the photon itself disappear and reappear. Instead, it is about transferring its precise quantum information. This information could be its polarization state to another photon located some distance away, almost like sending a perfect blueprint. Imagine a carefully arranged laboratory setup. In a typical experiment of this kind, scientists start with 3 photons. 2 of these photons are entangled, a special quantum connection we will explore soon. The third photon is the one whose state they want to teleport. This third photon interacts with one of the entangled photons. This interaction is carefully measured. The results of this measurement are then sent using conventional communication like an internet connection to where the second entangled photon is located. This information acts like a set of instructions. Using these instructions, scientists can then perform an operation on the second entangled photon. Remarkably, after this operation, this second photon takes on the exact quantum state of the original third photon. The original photon state is destroyed in the process of measurement. So the information has effectively jumped from one photon to another, even though the photons themselves did not physically travel that path. Experiments in Tennessee have successfully demonstrated this process, often over significant distances using optical fibers, similar to those carrying our internet data today. The significance of such experiments is profound. Each successful teleportation, especially over longer and more practical distances, is a crucial proof of principle. It shows that our understanding of quantum mechanics is accurate. It also demonstrates that we can harness its strange properties for real-world applications. These Tennessee experiments and others like them are vital steps. They pave the way towards building large-scale quantum networks. These networks could one day connect quantum computers or provide communication channels secured by the laws of physics themselves. They are truly quantum leaps. Section 5, Cosmic Twins, the magic of quantum entanglement. At the very heart of quantum teleportation lies a truly bizarre and wonderful phenomenon. It is called quantum entanglement. Imagine you have 2 tiny particles, like 2 photons. Under certain conditions, these 2 photons can become entangled. When they are entangled, they are no longer independent. They become linked in a very special way. Their fates are intertwined, no matter how far apart they are separated. If you measure a property of one entangled particle, you instantly know the corresponding property of the other. It is as if they are communicating secretly. How do particles become entangled? One common way is to create them together in a specific process. For example, certain crystals can absorb a single high-energy photon. They can then emit 2 lower-energy photons that are entangled. These 2 new photons share a combined quantum state. Think of it like having 2 special gloves, one left and one right. You put each glove into a separate, identical box. You then send one box to a friend on the moon, while you keep the other. Before you open your box, you do not know if you have the left or right glove, but the moment you open your box and see you have the left glove, You instantly know your friend on the moon has the right glove. There is no need for your friend to open their box and tell you. This is similar to entanglement. Before a measurement, properties of entangled particles like polarization are not definite. But when you measure one, its state becomes definite, and instantly, the state of its distant twin also becomes definite. It takes on a state that is perfectly correlated with the one you measured. This happens even if they are light years apart. This interconnectedness is what makes entanglement so powerful. It is not just a curious feature of the quantum world, it is a vital resource. Quantum teleportation relies entirely on entanglement to transfer information. Quantum computers also aim to use entanglement to perform calculations far beyond the reach of today's computers. The very existence of entanglement challenges our everyday intuition about how the world works. It shows us that reality at the quantum level is far stranger and more interconnected than we might ever have imagined. It is a beautiful, puzzling magic. Section 6, Spooky Connections, Einstein's Puzzle and Instantaneous Links. Albert Einstein, one of the architects of quantum theory, was deeply troubled by entanglement. He famously called it spukhafte Fernwirkung. This translates from German to spooky action at a distance. Einstein felt that this instantaneous connection between two distant particles was just too strange. It seemed to violate the principle that nothing can travel faster than light. If measuring one particle instantly influenced another miles away, it looked like some kind of faster-than-light signal. This idea made him very uncomfortable. He thought quantum mechanics might be incomplete. Why did entanglement seem so spooky to Einstein and others? It challenged a core idea in physics called local realism. Local realism suggests two things. First, that objects have definite properties even before we measure them, realism. Second, that influences cannot travel faster than light, locality. Entanglement seemed to break this. The properties of entangled particles are not definite until measured, and the influence on the second particle upon measuring the first appears to be instantaneous. This was the heart of Einstein's puzzle. He suspected there were hidden variables, unknown factors, that predetermined the outcomes. For decades, this remained a philosophical debate. Then, in the 1960s, a physicist named John Bell devised a mathematical test. Bell's theorem showed that if Einstein's hidden variables existed, certain experimental results would be different from what standard quantum mechanics predicted. Many experiments have since been performed to test Bell's theorem. Overwhelmingly, these experiments have confirmed the predictions of quantum mechanics. They have shown that entanglement is real. Nature, it turns out, is indeed as spooky as quantum mechanics suggests. Local realism, as Einstein envisioned it, does not hold true. It is important to clarify something here. While the influence between entangled particles is instantaneous, this does not mean we can send messages faster than light using entanglement alone. If you measure one entangled particle, you instantly know the state of the other, but you cannot control what state your particle will take. It is random. To send a meaningful message, you still need to send information about your measurement result classically. This classical information travels at or below the speed of light. However, entanglement, when combined with classical communication, is the key ingredient that makes quantum teleportation possible. Section 7. Weaving the quantum web stable connections for tomorrow. While scientists have successfully demonstrated quantum teleportation in labs, there is a long road ahead. Moving from these amazing experiments to practical, everyday technology requires something more. We need stable and reliable quantum connections. These connections would form the backbone of a future quantum internet. Imagine a web of entangled particles spanning cities, countries, or even the globe. This quantum web would allow us to share quantum information securely and efficiently. Building this web is a major goal for researchers today. There are significant challenges to overcome in creating such stable quantum links. One of the biggest enemies is something called decoherence. Quantum states, like entanglement, are very fragile. Any interaction with the surrounding environment, a stray bit of heat, a tiny vibration, can destroy the delicate quantum connection. Another challenge is photon loss. When sending photons through optical fibers or even through the air, some of them inevitably get absorbed or scattered. This makes it hard to maintain entanglement over very long distances. To tackle these challenges, scientists are exploring various innovative solutions. One promising idea is the quantum repeater. Quantum repeaters would act like stations along a long quantum communication line. They would take a weakened entangled link and refresh it, extending its range. Researchers are also developing advanced error correction codes, specifically designed for quantum information. These codes could help protect quantum states from noise and loss. Furthermore, new materials and techniques are being investigated to create more robust and efficient sources and detectors of photons. If we can establish these stable quantum connections, the potential applications are transformative. The most talked about application is ultra-secure communication. Quantum cryptography, which uses principles like entanglement, can create communication channels that are theoretically unhackable. Another exciting possibility is distributed quantum computing. This would involve linking multiple smaller quantum computers together. This network could then perform tasks that are too complex for any single quantum computer. The quantum web promises a new era of information technology built on the deepest laws of nature. Section 8. Whispers across galaxies. The dream of instant cosmic talk. The speed of light, while incredibly fast, presents a huge barrier for communication across cosmic distances. Sending a message to our nearest star system, Alpha Centauri, would take over 4 years each way. For galaxies millions of light-years away, a two-way conversation would take longer than human civilization has existed. This is where the dream of faster, perhaps even instantaneous communication across galaxies arises. Could quantum phenomena like entanglement offer a way to overcome this vast cosmic silence? It is a tantalizing, though highly speculative, thought. Quantum teleportation, fueled by entanglement, allows the state of a particle to be transferred instantly. However, as we have seen, it does not allow for faster-than-light messaging by itself. You still need that classical channel to send the measurement instructions. So, simply having entangled particles spread across a galaxy would not let you chat in real time. But perhaps future discoveries might reveal new ways to use these quantum connections. The nature of quantum mechanics is still being explored, and there could be aspects we do not yet understand that might change this picture. Even if we stick to current understanding, the challenges of intergalactic quantum communication are truly immense. First, you would need to create and distribute entangled particles across millions or billions of light-years. Then you would need to maintain that delicate entanglement perfectly despite all the radiation, gravitational fields, and interstellar dust in between. Sending the classical information needed for teleportation would still be limited by light speed, and detecting single photons across such vast distances would be an almost unimaginable feat of engineering. The scale of these obstacles is hard to comprehend. Despite these colossal hurdles, the dream of intergalactic communication fuels our imagination. It speaks to our deep-seated desire to connect and explore. While instantaneous talk across galaxies remains firmly in the realm of science fiction for now, the study of quantum entanglement and teleportation pushes us to think big. It encourages us to question the limits of what is possible. Perhaps in the far-distant future, our descendants will find ways to use quantum mechanics to send whispers across the cosmic ocean. For now, it remains a beautiful and inspiring goal that drives scientific curiosity. Section 9. Lighting up the future. Next steps on the quantum road. We have journeyed through the fascinating world of light and quantum mechanics. We have seen how light, the universe's speed cop, also comes in tiny packets called photons. We have explored the mind-bending concept of quantum entanglement, Einstein's spooky action, and we have learned how scientists like those in Tennessee are using these principles to achieve quantum teleportation. They are sending the very essence of light, its quantum state, on an invisible journey. These achievements are not just scientific curiosities, they are building blocks for a future transformed by quantum technology. The immediate next steps for researchers in this field are clear. They will continue to improve the methods of quantum teleportation. This means working to increase the distance over which states can be teleported. They will also strive to improve the fidelity, or accuracy, of the teleported state. Making the process faster and more efficient is another key goal. Currently, teleporting quantum states is often a slow and painstaking process. Scientists are also working on teleporting more complex quantum states, and even the states of small groups of particles, not just single photons. Looking further ahead, the long-term vision is to build a global quantum internet. This network would connect quantum devices around the world. It could enable the ultra-secure communication we discussed. It could also link quantum sensors, creating networks with unprecedented measurement capabilities. And it could allow quantum computers to work together, tackling problems in medicine, materials science, and fundamental physics that are currently unsolvable. Once a global quantum network is established, the next dream would be to extend it into space, perhaps creating an interplanetary quantum communication system within our solar system. The journey of discovery into the quantum realm is far from over. Each new experiment and each theoretical insight brings us closer to harnessing the universe's most subtle and powerful laws. Understanding light, photons, and entanglement is not just about satisfying our curiosity, it is about developing tools that can profoundly reshape our world and our future. The path ahead is challenging, filled with difficult problems to solve, but the promise of a future lit by quantum technology is a powerful motivator. The quantum road is leading us to a new era of innovation and understanding.